I'm going to just give a brief background of SAR. I know that maybe half the people here haven't had much exposure to SAR, so I'm going to try and give a little bit of a background to put it into context. And then I'm going to cover SAR for flooding, surface water, wetlands and flooded vegetation, and water level monitoring, which are the main types of water resource applications that we're using SAR data for right now, and end with some concluding remarks. SAR, as I assume most of you know, that it operates in the microwave region, but it's really important to understand that. The long wavelength makes it all-weather capability, and because it's an active sensor, it transmits its own energy. It can acquire data day or night. And this real-timely data acquisition capability is real critical for many water resource applications if you want to time the data acquisition to the water cycle, which is very difficult to do using optical sensors because of cloud cover constraints. And another driver for us is the large commitment Canada's already made in SAR, in particular the RADARSAT 1 and 2 programs, and with the following Constellation scheduled for around 2018, we've had a long history and commitment to SAR data. And SAR is really well suited for water. First of all, it's got that timely data acquisition, as I just mentioned, and it also has very good water-land separation, because the SAR backscatter from water is specular and you have a very dark target, whereas most land gives some sort of distributed backscatter and it's a brighter target, so it's easy to see water in the landscape. And then secondly, unlike optical data, it'll penetrate through the vegetation, and so you're able to map flooded vegetation more effectively in the microwave region. And the two main target parameters that govern radar backscatter are the dielectric constant and the geometry. While the dielectric of water is very high in the microwave region, you can see in the little chart on the right, the dielectric constant of water is around 70, whereas the dielectric constant of most dry land materials is between 3 and 10. So you've got a lot of contrast whenever you got water in the scene. And indeed, sometimes we refer to radar as the water seeker. It's looking for that the dielectric discontinuity in the target, and that's where the main reflection occurs. And so it's also important to understand that in radar, surface water is specular, but bound water tends to increase the backscatter and make a brighter target. And so we use dark target thresholding for surface water, but bright target thresholding for flooded vegetation. And it's important to understand that difference when it comes to water resource applications. And it's often important to understand these different scattering mechanisms. On the top, it's illustrated for an upland forest type of environment, and in the bottom for a wetland environment. And in the wetland environment in particular, you can get that double bounce scattering between the water surface and the flooded vegetation. And that does a couple of things. First of all, it creates a bright target, which makes it easy to discriminate. And secondly, you can use that phase information to get at water level. And we're going to talk about that in a little later. We've been using SAR operationally for flood mapping at CCRS since about '97. This was the first operational use of it. Of course, every year the Red River floods, and every year we get to practice on the Red River. And I'm sure you've seen many, many examples of that. But we've also used it in a lot of other places where the flooding has occurred and they invoke the emergency charter, which brings us into action. So we have a group at CCRS that does this in an operational manner to produce these flood products. You can take that same approach and apply it to surface water monitoring to monitor the temporal and spatial variability in surface water. And in some environments that can be very extreme, not only within a year, but between years. And now, of course, with climate change, we're looking at decadal time scale changes. And radar is really a good tool for that because, as I mentioned before, you can time your acquisition to the water cycle. And so you can watch this effectively over time in both annual and seasonal kind of ways. Here's an example from the Old Crow Flats, and you can see the very extensive change in surface water over a couple of months period in the year 2000. We can also use it for effectively looking at annual change. Here we are looking at McClellan Lake up by Fort McKay, and you can really see the change in the shoreline over time using this same approach, where we're looking at 98, 2000, and 2005, and you can see quite dramatic changes in the lakeshore. So one of the reasons that we've been driven to look at SAR for surface water is the inadequate map layers that are available through other sources. If you go to the NTDB 50K water body layer, it's based on about 1970s photography, and while it's fairly accurate for some permanent water bodies, it certainly doesn't carry or map the transitional water bodies very effectively, and especially water bodies that have changed over time. Some of my colleagues at CCRS also produce high-resolution land cover maps with spot at 20 meters, but they only do this once every 5 years. And so you've got one snapshot over time of the surface water extent, and while it's very accurate for that one point in time, it doesn't give you any idea of the seasonal or annual variability in that surface water. And if we're talking about monitoring, that's what's important, is the change over time, not the status at any point in time. So we kind of got encouraged to do some work in Alberta through our Director General's oil sands program. And so we added the Peace Athabasca Delta test site to a project that we already had going on for InSAR and water level. And when I came out and met with Tom and others in setting up the project, it became apparent that they had a broader interest than just the PAD. And so we were encouraged to add Calgary and Edmonton to give more of a provincial scale. So we've been generating InSAR data stacks over these 3 sites for the last 3 years in support of some of this research project. And this year we've even added a more extensive data collection over southern Alberta in collaboration with Environment Canada to look at operationally implementing SAR surface water detection into the hydrology and weather forecast branches of the Environment Canada. So what we can do, the research was to do InSAR analysis for water level measurement. But many of the people that I was talking to told me they were really interested in changes in the surface water. And so we were getting data every 24 days throughout the ice-free season, and so we could generate this seasonal surface water change using this thresholding technique. So this shows the change in surface water from May through to November for the Peace Athabasca Delta region. And we just simply use a thresholding technique and identify water. In tomorrow's training, John and Valentine will go over this process in some detail and describe how it's done. We also did the same thing for Calgary. Of course, that was kind of an interesting story. We had a 3-meter data collection going on in Calgary in 2013, and we got bumped by the emergency response to the flooding in downtown Calgary. And they replaced, consequently, our data collection got dropped, and the emergency response group and MDA proceeded to gather 30-meter data that covered both High River and Calgary, but at that lower resolution, you really couldn't see the details of the flood. So it was kind of an interesting trade-off, and you can certainly see in the data that we have the change in the surface water over that time period as the snow melt and the rainfall accumulated, in particular in the pothole regions. And of course, those aren't really mapped in the NTDB water layer at all because they're transitional water bodies. And so it's really hard to get an accurate estimate of the water volumes coming from that particular case. And of course, everyone knows they got quite surprised last year. So the other thing that we've done quite a bit of over the past is use SAR along with optical data for wetland classification. I wouldn't recommend SAR by itself because optical data does a better job at separating some of the wetland types more effectively, but radar really does a better job on some of the flooded vegetation types, and in particular some new research is showing it's really effective at separating bogs from fens in a project that Bob Sleep is involved in with Rita Touzi, and I'm going to show that just briefly in a minute. This was done in 1990 in the Lake St. Clair Delta, and using a combination of ERS1 and TM data, we got a 95% classification accuracy for wetlands. In most of the work I'm doing now, I'm assuming there's already a wetland classification, a wetland inventory. And indeed, I think Alberta's wetland inventory is like 70% complete or something like that. So depending on if you talk to DUC or Amera. So at any rate, I think radar certainly can play a role there, but the real state-of-the-art for wetland classification is a combination of optical radar with a DEM for constraining it. I was mentioning the flooded vegetation aspect, and we can certainly use bright target thresholding to identify flooded vegetation, but we can even do a better job if we use the phase information. And RADARSAT 2 was one of the first civilian SARs to have a polarimetric capability. And it's really important to understand what polarimetry gives you. When you're looking at a magnitude-only image, you've got one channel of information, radar backscatter at that particular system configuration. When you're doing polarimetry or quad polarization, you really now have 5 independent channels because you've got the backscatter at the 3 linear polarizations, HH, VV, and HV. VH is reciprocal, so it's really only 3 out of the 4 polarizations. But you've now also got the 2 phase differences between the like pole and the cross pole. The like polarization phase difference and the cross polarization phase difference. So now you've got 5 independent measures instead of 1. And of course, if you're doing multivariate analysis, you're a lot farther along in the game. In particular, some targets saturate in magnitude, but the phase response will still vary. And so you can get more information longer using the polarimetric mode. And this is important for the flooded vegetation aspect. And we're not going to talk too much more about that during this workshop or tomorrow. We're focusing more on thresholding for surface water and interferometry for water level. But I think it's important to understand polarimetry has a big role for wetlands as well. And one of the things that we've been doing is we use a polarimetric decomposition approach, such as the Freeman-Durden decomposition, where we can identify surface, volume, and double bounce scattering. And the little diagram on the, I guess it would be your right, is from the New Brunswick area, and you can see between April and May a significant change in the surface water and in the flooded vegetation. The surface water is the dark target because it's specular scattering, and the flooded vegetation in this case has been coded in green for the double bounce. So you can really see the change between the flooded vegetation and the surface water between the 2 dates as the snow melt recedes through the system. We did a similar thing in Dongting Lake in China, which is really the water level changes by about 1 meter from the snow melt to the end of the summer, and you can really map the changes in the flooded vegetation. In this case, we just did a change between the double bounce and coded that to red, and you can see the area along the floodplain here that was flooded vegetation just after snow melt and dry in the summertime, and that's what shows up in the red. So if you're interested in ephemeral changes in flooded vegetation or looking at the delineation of wetland extent more effectively, this radar and polarimetric decomposition has a lot of promise. We've also been using compact mode and can do very similar results with compact polarimetry. And I'm not going to get into that today either. So here's an example from Whitewater Lake in Manitoba, where we've got the Freeman-Durden decomposition from May and another one from July. And in particular, the marsh shows up as that red color. And you can see 2 things by looking at the difference here. First of all, you can see because of the brighter red color in July, that the marsh has grown and developed more. And that shows up by the increase in the double bounce response. And secondly, you can see where some of the marsh has grown up, where it was open water in the May and now is marsh in the July. That would probably be the bulrush or the wild rice, which is more ephemeral than the cattails. So you can really look at the change in this flooded vegetation over time using this kind of approach. So another thing I mentioned earlier is the use of polarimetric decomposition, and in particular Touzi's decomposition. Rita Touzi works at CCRS and has developed a decomposition method, and he's working with Bob Sleep looking at that for peatlands. And Rita's phase appears to be particularly sensitive to water in the subsurface, and so this of course means L-band is preferred because you get better penetration. And with the ALOS data, which is L-band, he's been able to separate bogs from fens using this phase detection of the water motion. As many of you would know, bogs are stagnant and fens have water flow. Bob's interested in that because of the fire retardation characteristics of the fen versus the bog. And Rita's, of course, wanting to demonstrate how his decomposition is sensitive to this. We've seen it for a number of other applications where the L-band gives some significant penetration, and you can see some subsurface features, and that can really enhance your understanding of the overall system characteristics. And this is, I think, work is just early in progress. And Bob, I assume you're continuing this year with data collection? And
yeah, we're growing up in August.
Right. So there's a lot of promise in this, and of course the good news is ALOS 2 has just been launched and is undergoing Cal-Val now, and so we'll have a new source of L-band data starting for the principal investigators in next year. So we'll see some new ALOS 2 data over this region acquired shortly. And of course, when they're comparing it to the wetland inventory, there's quite a difference because many of the traditional techniques aren't really good at separating bog from fen, and it often requires in situ analysis to really complete the task. So the penetration capability of radar might really help bring along that capability to classify those types of wetlands. Okay, as I mentioned, our real focus, or my real focus from the research perspective, has been on InSAR for water level monitoring. And one of the side effects that's come out of this is looking at the coherence. The coherence is a measure of the similarity between two radar acquisitions. If they're entirely the same, the coherence is 1. If there's no correspondence between the two images, the coherence is 0. We like to have coherence on the order of 0.4 or 0.5 to be able to successfully unwrap the interferogram and get at the height changes, which is what we're trying to accomplish here. And in this case, we've color-coded the image so that we have red. This is from a stack of data from May to October, the same stack that you saw the surface water extracted from. And we coded the coherence in red, the average coherence, and the variation of the coherence in green, and the intensity in blue, and we used just the intensity average as the background. And we're in the process of looking into this more carefully, but I'm pretty confident that we can detect differences between flooded vegetation and ephemerally flooded vegetation using this kind of approach. And I think you can see all the wetlands pop out at you here using that coherence combination, and the different colors in the wetlands indicate the duration of their flooding. So I think this might be a real interesting topic to pursue if you're interested in ephemerally flooded vegetation or the changes in flooded vegetation over time in relationship to the wetland extent. Now, as I've mentioned repeatedly, the real research focus here was on InSAR for water level, and this schematic from the USGS just illustrates the principle of how that's achieved. When you have the change in height, that gives a change in the travel time, which gives a change in the phase, which can be measured to the millimeter level accuracy using InSAR techniques. So here's the stack from the pad once again, and the second row is the coherence. And once again, you can see how the wetlands pop up at you, in some cases permanently coherent, and in some cases the coherence comes and goes, and I'm confident that's related to the flooding status. And then we produce the interferogram from the coherence. And this is an animation of Barril Lake, and with the coherence on the right and the interferogram on the left. And first of all, it's important to notice that the coherence stays high, which means we can apply this unwrapping technique throughout the season to this wetland. Secondly, if you look at the interferogram, you see that there's obviously different water level changes around this wetland. It's not all one level changing, because the colors in the interferogram change. And that's because different portions of the wetlands are, the water levels changing different amounts over that 24-day period. This technique was first looked at and developed in Louisiana and the Everglades, and it was really surprising to see how much water level variation there was over water bodies that we before had presumed were flat. And this is due to flow obstructions, wind effects, local drainage changes. In one of our test sites, the beavers are the main cause. But you certainly can have a lot of influences on those water levels. When it comes to modeling that, this is really important, because only 1 centimeter or 2 of water level change can imply a very large volume difference in terms of the water flow. We have 4 other sites there, and this is just those interferograms, and generating these changes over the year time period. And I want to point out once again, the coherence is generally quite high for these wetlands, and secondly, the water level changes are quite dynamic, both spatially and temporally. And we take that water level from the interferogram and can turn it into relative height changes, and these are those outputs for in this case the color scale goes from 0 to 0.1 meter or 10 centimeters change, and you can see several centimeters change within the wetlands within a time period and between time periods, and I think that's an important observation. Now, we still have some work to do. I think the thresholding for surface water is operational. I think polarimetry for flooded vegetation is well understood, but sometimes there's still challenges in the data and tools and knowledge, so it's still being developed. And this InSAR is a relatively new research area, so it's further away from operational implementation. But I'm confident by the Constellation kind of time frame, we can get operational surface water monitoring using SAR as one of the primary inputs. It wouldn't be the only input. The state of the art nowadays is multi-source for any operational application. But I think with the large commitment the Canadian government has already made to radar, and with the upcoming Constellation mission, it's really an important source of data that we should be considering. I think our investment to date is about $1.5 billion. Well, I think MDA would have a much better idea what that number is. So just real briefly on the Constellation mission, it's going to be quite similar in many ways to RADARSAT 1 and 2. It is going to have a few changes that are important to consider. First of all, with being a constellation, it's going to have 3 satellites, and we'll have 4-day repeat coverage instead of 24. That's a real important fact for the water monitoring. I think on a 24-day repeat, you're really not getting enough observations to monitor effectively. But when you start looking at it twice a week, you're going to have a much more effective data set. And then secondly, it's also going to have a compact mode. And unlike the polarimetric mode, the compact mode can operate without reduction in swath coverage. So in the Constellation, we can have a fairly large swath with a medium resolution and compact polarimetric data, which will allow you to apply all of these approaches I've been showing: thresholding for surface water, decomposition for flooded vegetation, or interferometry for water level. And of course, The 3 operational drivers for the Constellation are ecosystem, disaster, and maritime. And I'd like to point out that our water resource applications applies to 2 of those drivers. First of all, the ecosystem monitoring, and secondly, disaster management. Flooding is our biggest cost of disasters in Canada annually, and it happens every year. So I think it's certainly an important thing for us to pursue. So as a concluding remarks, I'd just like to mention that SAR and water resources is a real fit because of the dielectric constant implications on the radar backscatter and the timely capability of acquiring the data. With the Constellation planned, we have continuity. We'll have data from 95 on, and so you can start looking at long-term changes, not just annual or seasonal changes. And of course, water is becoming an importantly valuable commodity. Canada is sitting on a large portion of the water resources, so I think we have to become more responsible in managing it and eventually marketing it, I'm afraid. And so CCRS is continuing to collaborate with other partners and clients on water resource applications. Our department really has the mandate to map surface water, and Environment Canada has the mandate to monitor surface water. So it's been kind of a challenge between the 2 departments to decide who does what and when. And of course, when you get talking at a managerial level, you can often confound monitoring with mapping, and so it becomes quite a challenge. Nonetheless, we're working real closely with Environment Canada on many of these aspects, and we're hoping to move forward to have more of a national approach to water. It's been really a fragmented target, but I think with its increasing value, we're going to be forced to have some re-evaluation of our water policies.